Good afternoon, everyone. I am Mr. Ish. Thank you for joining me for this video. I have presented a very lengthy video on indeterminate forms, limits, and L'Hopital's rule right before this video. And I understand that video became quite lengthy, and I'm afraid that because of its length and the complex nature of the video concepts that were presented, many of us might still remain confused after that video, which is why I'm presenting this other more summarized version of that video where I will try to hopefully clear out any confusions or misconceptions that might have arisen from that video. When we're talking about indeterminate forms, we're thinking directly or indirectly of the L'Hopital's rule. Now remember, when it comes to limits, the use of the L'Hopital's rule is voluntary. It's not necessarily a requirement. The only requirement that arises with regards to that specific L'Hopital's rule is that when you use it, you're using it for the right indications. Don't arbitrarily use it for any form of limits other than what it was designed to be used for. The L'Hopital's rule is used directly or indirectly for indeterminate forms that arise with your function. The most basic form that you will see is this: 0 over 0, or positive minus infinity divided by the same. And this you will see in those types of questions which are kind of representative of rational functions, where you end up having a 0 over 0 or infinity divided by infinity. When this is a case of the indeterminate that you're seeing, then freely use the L'Hopital's rule, where you would, let's say L'Hopital's rule LH, we'll abbreviate it as LH. In the L'Hopital's rule, then you end up using the derivative procedure to end up arriving at your said value or your stated value that you're trying to meet. And you know, in these type of questions, you have limit as x is approaching some value. When x is approaching that value and you're testing that value out into your question over here, you end up having a 0 over 0 or infinity divided by infinity, and then you come up with some value over here after the derivative procedure. You can keep reusing this derivative procedure as often as needed, so long as every time at the end of each step, when you're doing the test value, at each step you're still arriving at this indeterminate form of 0 over 0 or infinity divided by infinity. So every time you're doing the L'Hopital's rule, keep testing your value, this value here, to see if you keep arriving at the indeterminate forms, and then you can keep using the derivative steps until you no longer need to. But these right here are the basic indeterminate forms, and by basic I mean the most common. We also saw other forms of indeterminates. The most other commonly one seen were the indeterminate product types. You know, the product types, the indeterminate products had this type of an appearance: 0 multiplied by an infinity. It could be a positive or minus infinity. And the procedure over here was to convert the product type into some sort of a quotient. And you know, when you convert it into a quotient, which kind of means a rational function, a upper function divided by a lower function, you could do the L'Hopital's rule, and then you could carry it out through the same loop procedures of the derivative procedure, so long as these values existed, these indeterminate forms, 0 divided by 0 and positive minus infinity divided by the same. But to convert it to the quotient form, we had to do some procedure which was something like this: f divided by 1 over g, or you could do g divided by 1 over f. Another indeterminate form that we saw was that related to differences. The differences were less commonly seen than products, but you can also have this type of situation: infinity minus infinity, and you can convert these differences, the difference of two functions, f of x minus g of x. Here we have f of x times g of x. Here we have f of x minus g of x. That's how the differences arise. These indeterminate forms lead to a tug of war between the two possible limits that you might arrive at. Anyhow, for these differences, we could again convert it into some form of a quotient. You could do it again by means of some rationalizing procedure, a common denominator, or some factoring procedure, convert it into a quotient. Once you convert it into a quotient, you can carry it out via the L'Hopital's rule, and you could keep doing the loop procedure of derivatives so long as the new indeterminate form of 0 over 0 or infinity or divided by infinity met. You could keep doing these procedures so long as you didn't arrive at your final value. And lastly, we also saw indeterminate powers. You know, the powers, they were not too difficult, but they had the form of f of x to the power of g of x. When we had these type of forms, we converted this initial expression, and you know, these types of forms were like 1 to the power of infinity, infinity to the power of 0 or 0 to the power of 0. These were the forms you were seeing. And you could convert it by means of some sort of exponential or natural log property into a product type. And once you add it into the product type, you would carry out through the product procedure and convert it into a quotient by means of this f divided by 1 over g or g divided by 1 over f, and then you could continue it out through the L'Hopital's procedure. And I'm going to make a little asterisk over here, because once we arrived at this product form, after we converted the power to the product form, we could come back to this step over here and continue it into this form, the quotient form. So if you think about it, right here, the very first scenario over here, when you have a rational function, that's the most direct application of the L'Hopital's rule, because you can start doing L'Hopital's rule directly, given that you have these type of indeterminate forms at play. When you're dealing with products, differences, and powers, you have the indirect application of the L'Hopital's rule, because you have to convert or modify these forms into the quotients first. And then you can start applying the L'Hopital's rule. Even this product form here will become a quotient when you convert it through this framework over here, which is why I have the asterisk over here, combining it with this, and then you carry it on that. And we also know that once we are going down the L'Hopital's procedure, so long as these forms are seen, you can keep carrying out the derivative procedure as needed until you arrive at your final value. So keep all of these nuances in mind. I know it's a lot to see and a lot to grasp, but keep this in mind. You don't have to use the L'Hopital's rule for indeterminate forms if you do not want to. But if you're going to use the L'Hopital's rule, then use it properly and use it for the correct situations. The correct situations are those dealing with these indeterminate forms. And these are the indeterminate forms right over here, 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 and right over here. So in the remainder of this video now, we are going to be looking at questions from my single variable calculus textbook. And we're going to be looking at these limit questions. I'll present a thorough procedure of how we will go about the question in terms of the steps or the thought processes that are involved, so that any of the uncertainties or the lack of clarities which have come forth from the previous video will be vanished by watching this video. When you're looking at a question like this, no matter what the question is, the first thing you want to be thinking in your head by means of applying this value into your variable is whether we are dealing with an indeterminate form or not. Because if we are dealing with the indeterminate form, the L'Hopital's rule will come into play. When we roughly put this over here, we know we're going to end up with something which looks like e to the power of minus infinity, which is not an indeterminate form. So you have to use other means other than the L'Hopital's rule. When you're looking at this question, rewrite it as 1 over e to the 3x, because this is an easy question. Rewrite it by plugging the infinity into this place of the x. You're getting 3 times infinity, which is really the same thing as saying 1 over e to the infinity. The computation of this value is so small that it'll approach 0, and your answer will actually be 0, and you'll be right to state that 0 as being the limit of this function. For this question over here, limit as x approaches 10 from the left, natural log 100 minus x squared. Do not confuse the presentation of this as being an indeterminate difference form, because it isn't. Because if you look at this right here is all a single function with regards to the natural log. This right here is the result of a tug of war between two functions. We don't have two functions at play. We have a single function here at play. We're not dealing with an indeterminate form. And when we're not dealing with an indeterminate form, do not be thinking about L'Hopital's rule. Just think about plugging this 10 right in here. You'll get 100 minus 100. You'll get a natural log of 0, which is undefined. So therefore, think of a value smaller than 10, but something very close to 10, like a bunch of 9s repeating. And plug this value into this right here and see what happened. So I've taken all of these 9s as I can fit, and I've squared it, and I've saved this value into my calculator. When I save this value and I minus it from 100, I get this 2 times 10 to the minus 8, and when I do the natural log of it, I get a minus 17.7. So it's not a difficult concept here. When you're using this as your x value, you're getting a minus 17.7. You can imagine if you were to squeeze out more 9s into your calculator screen, if you could, this value would slowly but surely reach minus infinity. Why? Because if you just look at the regular graph of a natural log, and I'm not saying this right here is represented because we have translation going on here, but a regular natural log curve looks something like this. It's always proceeding here towards minus infinity with regards to the left aspect of the curve, and that's exactly what you would end up seeing over here. slowly but surely the y values would proceed towards minus infinity as you could add more 9s and then square it and minus it from 100. You get so close to 100 that you'd have such a small value in terms of decimals, like 0.00s, all of these zeros, and some number would pop up over here. When you do the natural log of this, you get a pretty large negative answer. Eventually it'd make its way to minus infinity. So the answer to this question is minus infinity. When you look at this question, limit as x approaches 3 from the left, e to the power of 2 divided by x minus 3. We have an expression over here in terms of an exponent. All of this right here is an exponent, but it's an expression. You know, when you're plugging in this value over here, you're getting e to the power of 2 over 0, e to the power of undefined, but we're still not dealing here with an indeterminate form in the true sense that you have to use L'Hopital's rule. All you got to do in this case, when you're not using L'Hopital's rule, is you use your other techniques. One technique is just to get a value so close to 3, but from the left side. And you know, if this right here on the number line is 3, from the right side I'm looking at a value 3.0001, but from the left side I'm looking at a 2.9 and then 9. Keep repeating these 9s. 2.99, and that's a value you want to use. You want to plug in that value right here in place of x, and let's do this here entirely on the calculator, and we can do it. We'll take this value 2.9, as many 9s as I can fit on my screen, will minus 3. I'm getting a minus 1 times 10 to the minus 9, which I will save. I will divide that saved value, because it's 2 divided by that, and I get this minus 2, and I guess it would be a billion. You'll do e to the power of this, which is really saying like 1 over e to the power of 2 billion, 1 over such a large number that it would zero out, and that's exactly what you'll get. It will zero out. So your answer to this limit, based on approximation of values or the use of your calculator, is 0, because you ended up with a situation of 1 over e to the power of a very large number. And you know, 1 divided by a very large number is like saying 1 divided by infinity, it zeroes out. Except here I'm just using infinity in the conceptual sense. We really are looking at this over here. 1 divided by a very large number zeroes out, and that right there is your answer to your limit. This question over here will prove to be interesting. Limit as x approaches infinity. We have arc tangent x cubed minus x, and you know you can view this as inverse tan. X cubed minus x. Do not confuse this in terms of one of these indeterminate difference forms, because this again arises as a result of tug of war between two functions. We here only have a single function which is attached to a single variable. It's just a variable has been separated into two parts by means of a difference. So it by no means is this. We're not dealing with an indeterminate form. We're dealing with something which is quite determinate. You can handle this in one of two ways. You're basically thinking about doing on your calculator. You're thinking about this on your calculator, inverse tan of some value. You put that value and you hit your inverse tangent. See, you put some value and you do inverse tan. Shift tangent, you get the inverse tangent, and you can get to that answer. Or the other way is if you know the graph of an inverse tangent curve. You know the inverse tangent has a horizontal asymptote of y is equal to pi over 2, and here y is equal to minus pi over 2, and the graph looks something like this. As your values are proceeding towards the direction of infinity, which is what we see over here, the function is going to approach and get very close to this asymptote, pi over 2. So indeed your answer will become pi over 2. That's how you're determining the answer based on the graph. But how would we determine it if we didn't know the graph? It would be simple. You'd come up with some value, extremely large value, like as large of a value as you can do close to infinity. How about this? 1 exponent 99, and do inverse tangent and you'll get 90. The only reason being because you're conceptually arriving here on the graph so far away on this x-axis that in terms of the y-axis values you're very close to this horizontal asymptote, which represents pi over 2, that your value becomes pi over 2, which you know is 90 degrees. Another point to keep in mind with these inverse trigonometric functions is what was originally your x-axis values have now become your y-axis values. And remember, with the function and the inverse of that function, that's right here, minus 1 over here, and the inverse of that function, what happens is the domain and the range flip. If over here the domain is represented on the x-axis, here in the inverse graph the domain will be on the y-axis. If in the original function the range values are on the y-axis, in the inverse graph the range values will become on the x-axis. So keep all of that in mind. But right here, 90 degrees or pi over 2 is the answer for this question. For this question, if you look at it, limit as x approaches 0 from the right, natural log of hyperbolic sine function, you're not really dealing here with an indeterminate limit form, so you don't have to be thinking about the L'Hopital's rule. You have to be thinking about your question in terms of this. You're looking at natural log, especially if you don't have this function on your calculator, e to the x minus e to the minus x divided by 2, where if you were to plug in the 0, e to the 0 minus e to the minus 0 over 2, you could get an indication of what you're dealing with, and we can see exactly what that would be. E to the power 0 is a 1. 1 minus 1 divided by 2, you're basically looking at something like this. Remember, we're doing just the rough calculation. The natural log of 0 over 2, you're looking at natural log of 0, which you know is undefined. It's undefined. So we know we can't use zeros. We have to use a value close to 0 but from the right. How about a value we can do as many zeros and then a 1? And we run this value in place of x right here and in your calculator, and we can do that. If I take this value 0.0, as many zeros and then a 1, and I save this value, what's going to happen is I'm going to run this value to this formula right over here, then I'll do the natural log. So let's do it. When I do this, I get 1 times 10 to the minus 9 within the brackets, and when I natural log it, I get a minus 20.7. So with this value right here, I'm getting a minus 20.7. What's going to happen is as you add more and more zeros, this minus number will get more and more large in terms of further away from 0, but in terms of magnitude, it'll get larger, like negative values. You will eventually hit negative infinity, which would be the answer. This again is another one of those concepts where, with regards to the natural log curve, and this is not an accurate indication of this graph, but you're seeing in terms of the curve, you're heading down here towards minus infinity. Slowly but surely you're heading towards minus infinity, and that's what's at play over here. When you look at this question over here, limit as x approaches infinity, e to the power of minus x times sine x, one can make an error and say we're dealing with an indeterminate form, because if supposedly I were to do sine of infinity, I would probably get infinity, and e to the minus x can be viewed as 1 over e to the x, and when I do 1 over e to the infinity, I'm getting a 0. So I'm dealing with the 0 to the infinity type of form, an indeterminate form, and I'm looking at indeterminate products at play, so I should be using the L'Hopital's rule. But there's a slight error which is falling here into place, and the error is the sine of infinity is technically not equal to infinity because, and we're not technically dealing here with an indeterminate form, we're basically dealing with a form which is not indeterminate. You're getting something which will be of the form plus or minus 1, or any value between plus and minus 1, and of 0. And the reason why I'm saying this is a form which is at play over here, and it's not an indeterminate form, because if you look at the sine curve, that's why knowing the graphs sometimes is very helpful. If you look at the sine curve, you know you're looking at a domain of minus infinity up to positive infinity, and you know when you're plugging in a value of any function, when you plug in the value, you get what is equal to the output, and the output is here the y value, isn't it, right? If you take a sine of some value, it'll give you the range value, which is your output. It'll give you your range. What you're putting here in terms of your domain, you're getting what you are getting with regards to the function a range value. If you think about sine of infinity, anywhere within this domain, from minus infinity to infinity, all the values go no higher than plus 1 and they go no lower than minus 1, which means the range over here is always from plus 1 to minus 1, and I could have written that the other way, minus 1 to 1. So sine of infinity would be some value really technically between plus and minus 1. It wouldn't be infinity, therefore you're not really dealing with an indeterminate form. So don't make that mistake that sine of infinity is equal to infinity. It isn't. Sine of infinity could be any value between minus 1 and 1, depending on where you ended up being on your curve. How you should view this question over here is this. Look at it as sine x divided by e to the x, because e to the minus x means reciprocal. So this is one of those situations where L'Hopital's rule should not be viewed as being your means for answering this question. Now think about it as this. You're doing sine of infinity, which could be some value between plus and minus 1 divided by e to the infinity. So you can think of this, a plus and minus 1 value, range value in the numerator, divided by an exceedingly large value. A small value divided by exceedingly large value zeroes out eventually in terms of its value. And 0 is indeed your answer for this limit, not an infinity or infinity, and you would be thinking about L'Hopital's rule. This is how you would view it. So don't make the mistake of this, that sine of infinity equals infinity. Depending on the sine curve, sine of infinity could be a value between positive or minus 1, somewhere in between there. So for this question, we're looking at this limit as x approaches infinity, 1 plus 2 to the power of x divided by 1 minus 2 to the power of x. Our first determination here should be for the question if we are dealing with an indeterminate form, and you can roughly think about it by plugging in this infinity. If you plug in this infinity, and you can see very clearly what you are technically having is 1 plus infinity divided by 1 minus infinity, and you're technically dealing with an infinity or infinity form, which is like a good indication for you to use L'Hopital's rule. Because of positive infinity, minus infinity, and the rule is usually plus and minus infinity anyways. So when you're using the L'Hopital's rule, you can use the derivative procedure in the numerator and the derivative procedure in the denominator. When you do the derivative of 1 plus 2 to the power of x and 1 minus 2 to the power of x, you know the derivative of these, the ones will zero out. 2 to the power of x will be 2 to the x natural log 2, and 2 to the power of x over here will be minus 2 to the power of x natural log 2. These will cancel out, and you could eventually put x as infinity over here. But you can see this is the same thing divided by the same thing, except you're having a minus 1 show out over here, because it's the same thing as saying a divided by minus a, you know it would be a minus 1. So this is just exactly that playing, and here your role would be in terms of saying that you have minus 1 as your limit over here. So minus 1 over here, and you still have to use the L'Hopital's rule. You only have to do the derivative procedure once though to get to your final answer. For this question here, if you were to put infinity in here in place of x to determine if you're dealing with an indeterminate form, you would notice that we are. You'd basically get 1 plus 4 divided by infinity to the power of infinity. You know, this right here would zero out. You'd basically have 1 to the power of infinity, which is an indeterminate power type. That's an indeterminate power type, and I've shown you why in the previous video it is. So you know you should be using the L'Hopital's rule after you've modified this. You want to modify it by using the properties of logarithms. If y is equal to this expression, then you know natural log y is equal to x. That exponent coming out as a coefficient times the natural log of 1 plus 4 over x. Now you have an indeterminate product type which you can run through the L'Hopital's rule. You will follow this scheme over here. One of these. So we have to use one of these schemes over here, then we have to end up running this through one of these, and I want to use this scheme over here. This one right here, where I keep the natural log in the numerator. I'll do natural log 1 plus 4 over x. I have to do the derivative of that, and then I have to do the derivative of 1 over x, because it's always 1 over that function. We'll do the derivatives of the numerator and the denominator and see what we get. When we're doing the derivative of the numerator, we'll get 1 over u using the chain rule, and I have to do the derivative of this. The derivative of 1 is a 0, but 4 over x is the same thing as saying derivative of 4 to the x minus 1, 4 times x minus 1, which will be minus 4 over x squared. If you do the derivative of this on the side on your paper, you'll see it'll be minus 4 over x squared for the substitution part. Here we have x to the power of minus 1. When you do the derivative of that, you get minus 1 over x squared. You can do all of this on the paper, and you'll see that this part is playing out right. When you put the u value back in, we'll get minus 4 over x squared times u, which was all of this 1 plus 4 over x, all divided by minus 1 over x squared. And you know technically you can put infinity when we're at the right stage. We still have to simplify all of this, so let's simplify it. We can cancel out these minuses because they'll cancel out anyways. The x squares will cancel out too. If you flip everything around, this is what you get: 4 over x squared times 1 plus 4 over x times x squared over 1. See, this x squared over 1, this x squared will cancel out. Likewise, the minuses would have cancelled out. What you end up getting is a 4 over 1 plus 4 over x, and you can put infinity in place of x. When you put infinity in place of this x right over here, 4 divided by infinity, this zeroes out. Eventually what you're left with is just a 4, but 4 does not represent your answer. It has to be modified with this part. Natural log y equals 4, therefore y equals e to the power of 4, and e to the power of 4 is your limit. Okay, e to the power of 4 is your limit. And I'll put the limit right over here, e to the power of 4, and that is my right answer, e to the power of 4. Here for this question, limit as x approaches 0, we have tan pi x divided by natural log 1 plus x. We should always be roughly putting in this value here in places of x to see if we have an indeterminate form. What we end up having is tan of 0 in the numerator, and we have natural log of 1. And you know natural log of 1 is a 0, tan of 0 is a 0. We're dealing with this indeterminate form, the basic indeterminate form for which the L'Hopital's rule can easily be applied. we have to do the derivative of the numerator and we have to do the derivative of the denominator. But in each of these cases, we kind of have a composite at play. We'll get a secant square u, which is a pi x, resubstituting, I'm doing this in my head, and pi. If we do the chain rule in the top, we'll get pi secant square pi x, f of u, d, substitution, if u is equal to pi x, f of u is equal to tan u, d or du tan u times du or dx pi x, and you would get this. Likewise for this, we would get 1 or 1 plus x. If you did this entire procedure over here, and you can put x equals 0. But let's see what happens over here when you put x equals 0. You technically have to put zeros here to see if this 0 over 0 form still exists. If the 0 over 0 form still exists, likewise infinity or infinity, you can do another round of derivatives. You can keep doing derivative procedures so long as those indeterminate forms exist. 0 over 0 or positive minus infinity divided by positive minus infinity. But I think we'll be good at this step. If you put 0 in places of x, we get secant square of a 0, which is just a 1. On the numerator, we get a pi. In the denominator, we put 0 over here, we get 1 over 1, which is 1. And our final answer for this function, as x approaches 0, this function will approach pi, and pi will be our right answer. For this question here, limit x approaching 0, 1 minus cosine x divided by x squared plus x. I'm seeing an indeterminate form at play, but it's not the hard one. If I put zeros in here, I get a 1 minus 1 in the numerator, because cosine of 0 is a 1. Here I get a 0. I have a 0 over 0 indeterminate form, so the L'Hopital's rule right here can be used. We just do the derivative of the items we're seeing, and we'll proceed from there. It's not going to be a hard question by any means, and that in the end will allow you to do your substitution with 0 in place of the variable. Derivative of 1 minus cosine x is sine x. You can run that through and you'll see it. Minus will be negated by the derivative of cosine, which is a minus sine x. Minus minus will become a positive. Here we get a 2x plus 1. Now we can put x equals 0. When you put x equals 0, you have to run it through. If you're getting a 0 over 0, you have to do another round of derivatives. But I'm not getting a 0 over 0. If I put a 0, I get, in terms of the sign, I get a 0 in the numerator, but I get a 1 in the denominator. I get a 0 over 1. So there's no need to do another derivative step. This leads to your final answer of 0, and that right there is your value for this function question right here. The limit of this function will be 0. This will prove to be an interesting question. Again, as always, in your head, you should be seeing if the limit question you've been dealt has or is in indeterminate form at play or not. And you do that very easily by looking at this value and you substitute into place of your x or your variables and you see what you got. When you put 0 over here, I get a 1 minus 0 in the numerator and I get a 0, so I know I'm dealing with this indeterminate form. This right here, or the infinity positive or minus, is the best form to deal with or look at because you go directly into the L'Hopital's rule. The other indeterminate product types or difference types or indeterminate power types are more difficult because you have to modify that so that you can come into somehow this form at play. But when you have this right from the very beginning, you don't have to do those modifications. The only modification you do is the basic derivative application in the numerator and in the denominator. And I'm going to do some steps here fast. If we're doing the derivative of the numerator, I'll get 4e to the 4x based on the derivative rules we know. And I'll get a minus 4 in the numerator. Here I'll get a 2x. Now, see if x equals 0 still generates. You still have to test this out. If you're looking at this form again, you have to do another round of derivatives. When I plug 0 over here, what happens? I get in the numerator, I get a 4 minus 4, which is a 0. In the denominator, I get a 0. So I'm still looking at a 0 over 0 form, so I have to do another round of derivatives in the numerator and denominator. Keep doing as many rounds so long as these forms still exist. When I do the derivative of this numerator and denominator, I'll get here 16e to the 4x divided by 2. And we know how to do derivatives. We're experts at that. So we can do some of these in our head. And you still test the value. You're no longer getting in an indeterminate form of 0 over 0 because now you get something else, so you don't have to do any more derivatives. At this stage you stop and you say let's do our test value and get our answer. When you put 0 over here, you end up getting a 16 over 2. You can do that mathematically on your own and your final answer will be 8 and you'll be right. So this question in terms of the function is exactly the same as the previous one, except that your condition has changed. It's no longer x approaching 0 but x approaching infinity. Again, run your value through. When you run your value through, you're basically going to get infinity over infinity in the numerator, and you have the basic indeterminate form, which allows you to use the L'Hopital's rule. Having this form, or the 0 over 0, is the best. It's like a gift, because you know you can definitely use this without too much modification. You do the derivative of the numerator and you do the derivative of the denominator as many times as needed, so long as these basic forms exist. When you do the derivative of the numerator, you know we're getting 4e to the 4x minus 4n over 2x, and you test your value here again for infinity. When you do the infinity here, you're again getting infinity over infinity. Just like in the previous question, you have to do another round of derivatives in the numerator and in the denominator. When we do all of that, we get 16e to the 4x divided by 2, and we can put an infinity over here. When we put an infinity over here, what happens? Now, contrary to your previous question, you're basically going to get an infinity over 2, and you'll get infinity as your final answer, and that'll be a good answer. You may not like the appearance of that as your limit, but it's good, because we can plug infinity right over here and come up with that value. Now for this question, limit as x approaches infinity, we have x to the power of 3 times e to the minus x. You know, the first question we're thinking is, are we dealing with an indeterminate form or not? If you were to plug infinity over here, you'd basically be looking at x to the power of 3, and you'd be looking at e 1 over e to the x, right? You can rewrite all of that. If you do infinity, you're getting infinity to the power of 3 and 1 over infinity. You're looking at this form right here, 0 times infinity. So you have an indeterminate product type. So yes, we are dealing with an indeterminate form, but it's a product form. You know, the product form has to be modified so that you can use the quotient rule, and the modification procedure is this. Either you use one of these templates, you're basically converting the product into a quotient, and then the quotient can be applied or affected by the L'Hopital's rule. Your biggest task over here is what's going to be the numerator, what's going to be the denominator, or which template you want to use, because that'll help you exactly in terms of how you tackle this question. I want to use this one right over here, f and g. I'll keep the f in the numerator and I'll do the g in the denominator as my quotient. So what I will do is derivative of x cubed in the numerator, and then I'll do the derivative, and don't make this mistake of forgetting this 1. And that allows you eventually to put infinity. When you do the derivative of the numerator, you're looking at a 3x squared. But here, 1 over e to the minus x is the same thing as viewing it as e to the power of x. And you're looking at the derivative of e to the power of x. And you do your infinity. When you do your infinity over here, you have to retest the value. When you test the value, remember when you're using the L'Hopital's rule after an indeterminate product or difference or power type, you're basically going to convert your forms into this. You'll keep running into these forms until you can come up with some conclusion over here. Here I'm looking at an infinity divided by infinity, this form. So long as I can keep getting infinity divided by infinity, I have to keep doing my derivative procedures. And I do another round of derivatives. I get a 6x over e to the x. And I can see if infinity is affected here by any means. When I put infinity here, I'm still looking at this form, infinity divided by infinity. So I can essentially do another round of derivatives. You can keep doing rounds of derivatives so long as these forms are at play. When you do another round of derivatives, you get 6 over e to the x. Now when I test my infinity value, I no longer have that means 0, and that right there is the value to your question. So the limit of this function right here, as x approaches infinity, will be 0. And you can see in this case, we converted an indeterminate product type into a quotient form, for which we had the indirect application of the L'Hopital's rule, because we couldn't directly apply it from the beginning. We had to do some sort of procedure, so then we can apply it. And then this form came into play, and you keep doing the derivative procedure so long as you keep seeing these forms. When you look at this question, limit as x approaches 0 from the right, x squared times natural log x, you should always do the rough application of your value, this value. You're basically getting a 0 times natural log of a 0, which is 0 times infinity. You're looking at an indeterminate product type. For these types of questions, anytime you're looking at 1 over zeros, and this is like a good technique or a hint for you to remember, anytime you're looking at a 1 over 0 or a natural log of 0, where you're thinking about this undefined, you can convert this into an infinity, and you can use that as your indeterminate form. Like here I'm getting a natural log 0, so I'm using that as an infinity. If I had like a 1 over 0 and a 0, I know I have a 0 and an infinity, this form over here at play. Anyhow, keep that in the back of your mind, because these two conversions of these two into this form right here will be very helpful for you for these types of questions. We're looking at an indeterminate product type. We have to convert into a quotient form, fg, and you know it's going to be f over 1 over g or g over 1 over f. You have to pick the right one over here, or the right one meaning which will lead you down to the easier path. I'll keep this in the numerator, so I'm going to go with g over 1 over f. Now this is why I'm saying it's an indirect L'Hopital's rule, because we couldn't directly apply it from the beginning. We had to do a modification which allows us to use the L'Hopital's rule, so you're indirectly using it. You're doing the derivative of natural log x, and you're doing the derivative of 1 over x squared. You can't forget this 1 over x squared, because I almost did, but I remembered it. The derivative of natural log x is a 1 over x. The derivative of 1 over x squared is the same thing as looking at as the derivative of x to the minus 2, which will be minus 2 over x cubed. You can do that alone on your paper on the side, and you'll see you'll get this as a derivative of 1 over x squared. When we're doing the derivative of this, we can eventually put x equals 0, but we have to first solve this out. Simplify it. 1 over x times minus x cubed over 2, and then we'll see. You will keep doing the derivative so long as one of these forms are at play, and you know 0 or infinity, positive or minus. You'll keep doing the derivatives in the L'Hopital rule so long as these forms keep coming into play with your substitution. But you have to first do your simplification. X can simplify with x cubed, you'll get minus x squared over 2, and you can plug in 0. When you plug in 0, we don't have this indeterminate form here coming into play at all. You basically end up having 0 over 2, which tells you your limit form here is a 0. So when we're looking at this question over here, and we don't have very many more left for this video, these are all questions that I told you from my calculus textbook. 1 plus a divided by x to the power of bx, x approaching infinity. You know x over here represents your variable, a and b values represent your constants. You have to start by asking yourself if we are dealing with an indeterminate type or not, or some form of an indeterminate form. And you know you can take the x approaching infinity and plug it into place of your x values and see what type of form we are dealing with. When you plug infinity here into your question, you know you zero out the a over x. What you are essentially left with is an indeterminate power type of 1 to the power of infinity. And you know when you're dealing with indeterminate power types, you have to be thinking about converting this into an indeterminate product type. And you can do that by invoking the natural log rule. Natural log y, because this y is equal to this function, is equal to bx natural log 1 plus a over x. Now you've converted into a product type, and what would happen if you were to plug this infinity in places of x's? You would get basically natural log of a 1 and b times infinity and natural log of 1, which is a 0. You've converted this into this type, and you can see that by plugging in infinities here in places of x. And remember very quickly, as I have mentioned, if I have not mentioned, I'll mention it here. Anytime you're seeing this or natural log of 0 for these type of questions, just think of it as you're dealing with an infinity. And you can use that in terms of your determination of your form. Anyhow, let's come back to the question. Here's our type over here, and we have to use the template FG, the product template. Even the indeterminate powers go to the product formation, and then the products go to the quotient formation. Everything eventually trickles down into the quotient form. As my introduction showed you, you have to use one of these forms. Here's my f, here's my g. You have to decide which one. I'll keep the natural log in the top. You can do the derivative, because once you're looking at it in terms of a quotient, you're thinking about the L'Hopital's rule and you're doing the derivatives. You'll do the derivative of the numerator, 1 plus a over x, and you'll do the derivative of the denominator, which will be 1 over bx. Now you have to do the derivative with regards to these variables over here, the x. When you do the derivative of the numerator, you know you'll get natural log u and then the derivative of this u substituent. You'll basically get over here derivative of 1. You know you're thinking of this in this way. If u is equal to 1 plus a over x, then f of u is equal to natural log u. Alright, and you have to do the derivative of this u, and you have to do derivative of ln u, and you know how to do all of that. You'll get 1 over u, which is 1 plus a over x. I still have to multiply this by the derivative of this 1 plus a over x. 1 plus a over x is really saying 1 plus a x to the power minus 1. Derivative of 1 is a 0, but derivative of a x to the power minus 1 will be minus a over x squared. You can do this on a paper and confirm, but that's what it'll be. Now when you're looking at this, I don't know, I have a natural log over here. This appears to be a mistake, but it's derivative of 1 over bx. 1 over bx. I'm basically looking at the derivative of something which looks like this. X to the power minus 1 over b. 1 over b can come out on the side, and we're basically looking at minus 1 over x squared. That's what we have. When we marry all of these things up together, we come down right here, we have 1 over 1 plus a over x times minus a over x squared. And here we basically have something here, minus 1 over bx squared. We can flip it around, bring it up, we will get a minus x squared b over 1. You can start cancelling things out. This x squared will cancel out with this x squared, this minus will cancel out with this minus. What you eventually end up with is ab over 1 plus a over x, for which you can start putting in this value over here. When you put this value over here in the denominator, you'll zero out the a over x. You'll essentially get left with this ab over 1, which is just ab. But we know ab is not our true answer because it has to be modified in terms of this. Natural log y equals ab, therefore y is equal to e to the power of ab. And we'll put it right over here, e to the power of ab. That'll be our final answer. If at any time you feel like I'm skipping through these derivative steps, it's fine. You can always do those parts on your paper. Natural log y is equal to ab, therefore y is equal to e to the power of ab, and that right here is my answer. The limit of this function as x approaches infinity is e to the power of ab. When you look at this question, limit as x approaches 0, we have this entire function here, a quotient basically, a quotient of two separate numerator and denominator sets of functions. It's going to be a good thing over here if we just plug in the 0 value over here in places of these x's and see what happens. We get 5 to the power 0 minus 4 to the power 0 divided by 3 to the power 0 minus 2 to the power 0. We're essentially getting a 0 over 0 indeterminate form, and we know we can use the L'Hopital's rule because we have this form over here, 0 over 0. When you do the L'Hopital's rule, it's easy because you're doing the derivatives now of what you're seeing in the numerator and the derivatives of the denominator. And you know this is not going to be anything hard. These are those power functions. You're doing the derivative of that. Remember, the derivative of b to the x was always b to the x ln b. If you remember that from your template scheme, when we're doing the derivatives of everything here in the numerator and the denominator, what we essentially get is 5 to the x ln 5 minus 4 to the x ln 4 divided by 3 to the x ln 3 minus 2 to the x ln 2. And when you do this, you can put in these zeros into these values after you're doing your derivative step. And remember, you can keep putting in these values and keep testing them to see if you're still having the indeterminate form play out, 0 or 0 or infinity. So long as those forms keep appearing up with you testing your values, you can keep doing the derivative step. When you do all of this in x's, you're putting these zeros, you do not get the indeterminate form anymore. What you really end up getting is this natural log 5 minus natural log 4 or natural log 3 minus natural log 2. That's what happens because all of these powers to the x, 5 to the power x, 4 to the power x, 3 to the power x, 2 to the power x, with the place of 0, they all become 1s. So this right here becomes your final answer. So the limit as x approaches 0, this function right here, or this curve, will approach the value. And you can get a calculator value over here. You just have to do the numerator divided by denominator. What this value ends up being over here is 0.5503. It's just the calculator value of all of that. When you look at this question, limit as x approaches pi over 2 from the left, secant x minus tan x, we know we have here two functions which are competing in some form in terms of the limits that they'll bring. And there's a difference over here, so we might have an indeterminate difference here at play. But how do we know whether we really have an infinity minus infinity at play, an indeterminate difference form? We do have that, but how do we really know that? You can know that by looking at the graphs of these, and you can just do a little graphic exercise. You know, when you're looking at the cosine graph, here's pi over 2, and let's not go too far in terms of the domain. And 1, the cosine graph looks something like this. This is just part of it, and you know it's going to extend out here and extend out here. And you know, when we're talking about the reciprocal of the cosine, we're dealing with the secant, and we end up having a asymptote develop here, and then the secant curve pops up in that direction here, just a secant curve right here. For this little part, you have a reciprocal, and you know here your secant curve will come over here in this direction. Anyhow, what are we seeing as x approaches 90? Here's my 90 value, 90 over here. As the curve approaches 90 from the left, what's happening to the curve? It's approaching positive infinity. So we know we're having here a positive infinity here if we just put this value here. What about the tangent curve? When you look at the tangent curve again, let's just look at the pi over 2 and the minus pi over 2, because these form vertical asymptotes. The only reason why we're seeing vertical asymptotes because in terms of the secant, we're looking at a 1 over cosine x. We are looking at 1 over cosine 90, which is the same thing as 1 over 0. And for the tangent, we're looking at a sine over cosine. We're looking at sine 90 divided by cosine 90, which is really looking at 1 over 0. You see we're getting undefined here, we're getting undefined here. That's why we're seeing that vertical asymptote. But the tangent curve right here would be something like this. As x values are approaching pi over 2 from the left, your curve is approaching positive infinity, right here, positive infinity. So you have an infinity minus infinity, this indeterminate form playing. So when we know we have this form playing, we have to somehow convert it into a quotient so that we can start thinking about the L'Hopital's rule application, and that's what we will do for this question. So when we're dealing with these indeterminate difference forms, you know we can use rationalizing, you can use common denominator or factoring. You won't see too much of the other techniques, but you'll see much more of the common denominator here at play. And we're going to use a common denominator to convert this into a quotient form. Look, 1 over cosine x minus sine x divided by cosine x. Once we convert it to quotient form, then we'll do the L'Hopital's rule. You have a common denominator of cosine x, you have 1 minus sine x. Now, if supposedly you put pi over 2 over here, what are you going to get? You'll get, technically, you'll get 1 minus 1, which is 0, divided by cosine of 90, which is a 0, and you've converted this indeterminate form into this form, for which you know the L'Hopital's rule is very easily prescribed. You'll do the derivative here for the numerator aspect, and you'll do the derivative here for the denominator. Here's my numerator, here's my denominator. What's the derivative of 1 minus sine x? It's minus cosine x. And you know that because it's sine x is positive cosine x, but it's impacted by that minus. The derivative of cosine x is a minus sine x. And when you do the derivative procedures, you're able to plug in your value. You can cancel out these minuses. You're looking at basically cosine x over sine x, or you can say x here equals pi over 2, or you can say you're looking at tan x, right? Tan x at 90 degrees. The better way to look at it is in this form right over here, because what would happen if you did 90 and you tangent it? If you do a 90 and you hit tan on it, what happens is you get undefined, right? But if you look at it in this form where you've separated into its functions, you're looking at cosine 90 divided by sine 90, because you can technically put these values in. You no longer have an indeterminate form. You have a 0 over a 1 form, a 0 over a 1 form. It's not this, so you don't need to do another round of derivatives. 0 over 1 will give you to your final answer. It'll lead you to that. It's 0. In this way right here, you could have thought about it in this form, but you have to think about it that you're beginning an undefined over here. When you break it here into its sub-functions, cosine and sine x, you get the better procedure outcome from there. And your final answer here is a 0. So this question is done. So I want to end the video here with these following notes. When we're talking about indeterminate forms, especially the L'Hopital's rule, you know L'Hopital's rule is optional. But you want to use it, but it has to be for the right reasons, where you're seeing positive or minus infinity divided by infinity, or you're seeing 0 divided by 0, and here is positive and minus in the denominator. You don't want to just use it arbitrarily for any form. You want to use it for indeterminate forms, especially of these two. When we're talking about the products, and you know the products are of this form right here, 0 multiplied by infinity, you convert it into a quotient, right? So that then you can start using the L'Hopital's rule, so long as you see these at play. Normally all the indeterminate forms are converted into some form of a quotient, and you know that. When you're seeing the differences at play, the indeterminate differences, and you know that's this infinity minus infinity, you're going to convert it again into some form of a quotient, rationalizing, common denominator, factoring, so you can use the L'Hopital's rule. L'Hopital's rule can be used as often as needed once you have the appropriate form at play, and so long as the form keeps coming into play. And for the powers, then indeterminate powers, something which looks like 1 to the power of, let's say, infinity, 0 to the power of 0, or infinity to the power of 0, you will again convert it first to products by means of some sort of law of logarithms or exponentials, and then from the products you're going to convert it into quotients, and you will do that, and then you will look at it in terms of the L'Hopital's rule. And the procedure for converting products into quotients, is this: fg is equal to f divided by 1 over g, or g over 1 over f. Eventually everything will be converted into some sort of a quotient, and by quotient we're talking about rational functions, and then from there you'll be using the L'Hopital's rule. So keep all of that in mind. I hope you enjoyed this video. Hopefully it made some more sense than the previous video and there are no confusing concepts remaining. Remember, this right here, all of it is optional. You don't have to use it, but if you're going to use it, make sure you're using it for the right reason or for the right indication. Otherwise you'll end up with a wrong answer. Thank you for watching. Have a nice day. Bye.